Hello, this is a video lesson on the X-ray tube. So let's begin with the X-ray tube being called a diode tube. Diode stands for Di stands for two, and ode stands for electrodes. There are two electrodes, and that's the cathode and the anode. So we have a diode tube in diagnostic radiology. What is the purpose of the protective housing? Well, the protective housing is that part that surrounds the X-ray tube, and it has a lead equivalency of 1.5 millimeters that's going to surround that area, and the purpose is to limit leakage radiation. Leakage radiation is radiation emitted anywhere but the tube window, and that what comes out of the tube window is the useful beam. So what is the purpose of the glass envelope? Well, the glass envelope is in the diagram down here. That's the glass envelope, and the purpose is to provide a vacuum. We don't want any air inside the X-ray tube. Let's talk about the parts of the cathode. So starting off with the focusing cup. The focusing cup's a metal cup in which the filaments are embedded. It's negatively charged to condense the electron beam to a small area of the anode. The materials are moly or nickel. Its functions are to focus or concentrate electrons into the space cloud and concentrates the electron beam to a small area of the anode called the target. So if we take a look at the top picture, this picture here is showing a filament without a focusing cup and how the electrons would be splayed. On the other hand, with the focusing cup, the electrons are concentrated toward the target on the anode. And then down here just showing that the negative charge on the focusing cup. The filament, which there are two, is a coil of wire that's usually about 2 millimeters in diameter and 1 to 2 centimeters long. The composition is thoriated tungsten. There are two, like I said. This is the small filament, and this is the large filament, and just showing how the electrons are going to be going over a smaller area with the small filament and over a bigger area with the large filament. So the material is thoriated tungsten that's used in diagnostic radiology units. We use tungsten because it has a high melting point and a high Z number, which is 74. It has 1 to 2% thorium, which is increases the efficiency of thermionic emission and prolongs tube life. Now we have what is called a dual focus tube. Because we have a small and a large focal spot, which means we have a small and large filament, we have a dual focus tube. The small focal spot is selected by choosing the small filament. It's used with lower MA stations such as 3 MA or less, and it's going to increase spatial resolution is the advantage. The large focal spot is selected by choosing the large filament. It's used with higher MA stations such as 400 MA and above, and it dissipates heat. We have a lot of heat produced when we produce X-rays, and so it's going to help with that process. So again, this is called a dual focus tube. Now the anode, on the other hand, we have the target, and that's the area of the anode struck by electrons and the precise point at which X-rays are produced. In the stationary anode, which is the first one shown, the area where the tungsten is located is the target. On the rotating anode, which is the one below, the target, we have a focal tract, but the target ends up being down here, and this area all the way around is called the focal tract. So the rotating anode is going to spread heat over larger areas so higher mass values can be used. Our weight of a normal anode disc is 700 grams, and we have common diameters of 3, 4, or 5 inches. As far as the speed of the rotating anode, an average speed is 3,400 revolutions per minute. If you have a high-speed anode, which is common in angiography, it's around 10,000, approximately on average, 10,000 revolutions per minute. The target itself is that focal tract on the rotating anode of where the area where the electrons are strike the anode, and those electrons are coming from the cathode and strike it. So we have pitting or tracking that always occurs in this area. So the materials and parts of the disc, we have the first part, which is the face of the disc, is comprised of the tungsten and rhenium. That's the face of the disc here. That's the part that faces the cathode. So the tungsten makes up 90% of the anode disc and rhenium makes up 10%. The reason why we like to use tungsten is, first of all, it has a high atomic number. Secondly, it has high thermal conductivity. And third, it has a high melting point. The reason why we use the rhenium is because it provides a smooth surface when a high-speed electrons strike it to provide more uniform density. The next area that we have is the graphite, moly. Moly is right behind the tungsten and rhenium. So it's right behind it. And that's going to just be a good area for being able to conduct heat, being able to handle heat. The last part is the graphite, which is the lower part, and that's used sometimes in the layer behind the moly in the disc, again helping with heat. The stem, which is the piece that's the part that's right behind here, that piece right here, that's called the stem, and it's comprised of moly. And then the induction motor is the part that's going to have the rotor is going to rotate the anode. The purpose is it dissipates or distributes heat, and the ball bearings that are inside of here, which are showing in the picture, the bearings, those are made of silver plating. Now the stators are outside the glass envelope. They're neutral. That means that there's no charge, of course. They're outside the glass envelope, and electricity is brought to the stators, which causes the rotor to spin. Now, if we take a look at this, we have the first part is the rotor. That's the part that's in here. That's the part that we want to spin the disc. And that's also shown from this perspective as the rotor. Okay, then we have the next part is right around the rotor is the glass envelope. It looks small on this diagram, but here it is up here. So it's going to be the vacuum that we're going to have. So the rotor is inside the vacuum tube. And then outside that are going to be the stators. So they're up here. There's only two shown from the 2D perspective. And when they turned it on end, we can see the true number of them. So there you go. We have a total of 8 of them. And as I said before, the stators, electricity is brought to the stators, which causes the rotor to spin. It's called an induction motor because there are no touching parts. The anode warm-up procedure is the medium kVp, approximately 70 kVp, and MA is low, about 100 MA, and a long time, approximately 1 to 2 seconds. And that's something that manufacturers sometimes just have a button for you to push versus having to set the time or set the kVp or the MA. But it's just that's what the warm-up procedure ends up being, is approximately those values. And you can repeat those exposures once every minute for 3 minutes. On the anode, we have, first of all, the electron beam size, and that's the area from which electrons are coming from the cathode. So that's the electron beam. That's going to be dependent upon the size of the filament, whether we use the small or the large. So the second part is called the actual focal spot, and that's the part where the areas that are struck by electrons, and how you find that is you draw a line perpendicular from the anode from each edge of where the electron beam was. The effective focal spot, which is the last part, is the area from which X-rays are emitted. I'm just going to drop a line down directly from each edge of the actual, and that's the effective focal spot size, also known as the projected focal spot size. The line focus principle states that by angling the target, the effective focal spot size is much smaller than the actual focal spot. So if we look at the picture on the left-hand side, we can see that we have 24 degree angle versus 12-degree angle on the right-hand side. And so we're able to make our angle, our effective focal spot size, much smaller on the right-hand side. And then just to show that the smaller the angle, the smaller the effective focal spot size. And if we increase the angle, which is a 24 degree, we're going to have a larger effective focal spot size. If we increase our filament size, if we go from a small filament size, which is shown here, this one's considered small because the electron beam is small, then we're going to have a smaller effective focal spot size. On the other hand, if we have a larger filament that was used, we have a larger electron beam size, that means our effective focal spot size is larger. So if you increase the filament size, you have a larger effective focal spot size. Another thing is that if you have a narrow angle or small angle, as you do on the right-hand side over here, you're going to have a more narrow or useful beam. So that's the only thing. We have to make sure that we use at least a 12-degree angle at 40-inch SID, at least a 12-degree angle. Next is we have the anode Heal effect. The anode Heal effect is that we have less X-rays on the anode side and more X-rays on the cathode side. So what happens is the X-rays are filtered out by the anode. They're eaten into it, so X-ray intensity is increased on the cathode side. So at the central ray, we're going to have 100% intensity, but on the cathode side, we have 120%, which is much higher. And then on the anode side, we only have 75%. So that cat, we're going to make sure that we put the bigger part under the cathode. And so we can see on this picture here that we've got the X-rays are being eaten into the anode, and that's why we have less X-rays on the anode side. And like I said, we're going to put the thicker part, which is T12, over the cathode over the thicker part, which is fat cat. And that way we can even out the receptor exposure versus what we have on the left-hand side. So we put the cathode on the bottom and we put the anode up here. The anode is over the thinner part, the cathode over the thicker part. And then finally, the smaller the angle, the more Heal effect that we see. So that's the one thing that we have more of a narrow beam is going to result in more of a Heal effect. Off-focus radiation is radiation produced anywhere but the focal spot. And so that's they're called extrafocal rays. So something we can do to help prevent that, to reduce off-focus rays, is the first set of collimators is called a diaphragm that fits up into the protective housing on the collimator. And that helps to reduce off-focus radiation. And then this is just a picture showing what off-focus radiation is, or what it looks like. There's more on the anode side than there is on the cathode. And then this is the actual off-focus radiation in this picture. X-ray tube failure. The most common causes of X-ray tube failure is excessive heat, and that results in decreased tube life. Now, as far as X-ray tube failure, we can have that as an issue from both the filaments and from the anode. So filament factors involve excessive heating of the filament caused by high Ma used for prolonged periods vaporizes the filament. And the results are vaporized tungsten that coats the inside of the glass envelope. This causes electron arcing from the filament to the enclosure because the electrons will be attracted to the tungsten. It causes filtering of the X-ray beam, which means we have less X-rays coming out as part of the primary beam, and it interferes with the electron flow from the cathode to the anode. Secondly, the filament wire becomes thinner and eventually breaks, producing an open filament, kind of like a light bulb when you break a filament inside of a light bulb. Anode factors due to excessive heat include melting and pitting of the anode that causes variable and reduced radiation intensity. The anode can crack, becoming unstable, and rotation is the second one. A third one is similar to what happens with the filament is vaporized tungsten coats the inside of the envelope due to the melting and causes arcing. And lastly is bearing damage is that long exposure time causes excessive heating of the anode resulting in damage in the bearings, and it causes warping and rotational friction of the anode with a loud grinding noise and wobbling of the rotor. On the left-hand side is the pitting that can occur due to excessive heat, and on the right-hand side is a bullet-like melt. And the bullet-like melt happened because the anode stopped spinning and just had that one location that was continuously being struck with electrons and being where production of heat and X-rays was occurring. Compensating filtration. So it produces an image with a uniform average receptor exposure when examining a body part that varies greatly in tissue or a thickness or tissue composition. And what you want to do is put the thick part of the filter over the thinner body part. So in this case, we put the thicker part of the wedge filter over the toes. So this is called a wedge filter up here. And the trowel filter, we're going to put the thicker part over the lungs. So a trowel filter, we put the thicker part of the lungs for a chest x-ray. And then we have a bow tie filter, which is used in CT, and we have a conic filter used in digital fluoroscopy. Last but not least is the idea of exactly what happens after X-rays are produced and what happens to them. So the path through which X-rays travel after being produced at the anode. So the first things they do is they're going to pass through the glass envelope. So this is the glass envelope is the very first thing. And then right after that, we have the oil. So the oil is in between here. And in fact, it's all the way around the X-ray tube itself and within the protective housing. And then we're going to have the filtration is next, which is the letter F here. That's comprised of aluminum. And then in the path of the collimator box is the mirror. And so that acts as extra filtration as well. It's actually 1 millimeter of filtration as well. And this concludes our lesson on the X-ray tube.